All right, this is our first lesson of the chapter in sequences and series, and this is an introduction to sequences. So first off, what is a sequence? A sequence is an ordered list of numbers. It's a relationship or function in which the domain is the set of natural numbers. In general, a sequence is a pattern or a ordered list of numbers. So right here and right here, right here and right here, that is two examples of sequences. This right here is a sequence that ends, right? It goes 1, 3, 5, 7, 9. The end. That is a finite sequence. And then here is a sequence, 1, 3, 5, 7, comma, dot, 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 meaning it keeps going on forever and ever. That's an infinite sequence. Each number in the sequence is called a term. It was hard for me to say number because I want to call it a term. So this is the first term, the second term, third term, fourth term, and fifth term. This has an infinite amount of terms. For a sequence, the number of the term is represented by n, okay? So when I say n equals 1, right, that means that there's one term. N equals 50, that means there's 50 terms. The value of the term is represented by a sub n, and that's the number that sits in the nth position. So the whole entire function is called a sub n, but then talking about the value of the term, so like if there was a 1 here, that's the first term. So this is a sub 1, this is a sub 2, this is a sub 3, a sub 4, and a sub 5. So the first, second, third, fourth, and fifth term. Here it says, consider the sequence defined by the formula a sub n equals 3n minus 7. If a problem said to find a sub 10, what do you think that means? It means find the 10th term. And in order to do that, you are going to do a sub 10 is equal to, and then you're just doing 3 times 10 minus 7. So the 10th term is 23. And that's how we write the 10th term is 23. This also gives us an ordered pair, like an x comma y value, which is really an n comma a sub n value. So 10 comma 23. Okay, so this, just like the tile patterns that we did in our last lesson, this is recognizing patterns and then finding the next 4 terms of each sequence. So I'm looking for the next 4 terms. So 1, 2, 3, 4. All right, so I need to find out what the pattern is. So if you look at this pattern here, 16 is half of 32, 8 is half of 16, 4 is half of 8. So the pattern is to multiply by a half. So I'm going to continue to multiply a half. Half of 4 is 2, half of 2 is 1, half of 1 is a half, and half of a half is 1/4. All right, let's look at the next one. I need the next 4 terms, so I like to put little spaces for them, just so I don't forget any of them. If I look at my pattern here, I have 1, 2, 4, 7, 11, 16, 22. So here, this is add 1. This is add 2, add 3, add 4. So I got my pattern here. Add 5, add 6. So I'm going to add 7, which is 29. Going to add 8. Oops, that looks like 18. Add 8, which is 37. Add 9, which is 46. And then add 10, which is 56. Okay. All right, so this next part right here, this is also write the first 4 terms of each sequence, but this time we're given a rule or an equation to follow. So this says find a sub 1. So what you're going, this is like directing you in the right direction here. To find a sub 1, we're going to plug in 1 for n, and we get 9. And then we're going to plug in 2 for n. 2 times 2 plus 7, we get 11. So I'm just making it as a list for my final answer. Plug in 3. 2 times 3 plus 7, and I get 13. And I plug in 4. 2 times 4 plus 7, and I get 15. So my first 4 terms are 9, 11, 13, 15. Now, if you look at what the pattern is there, it's plus 2, plus 2, plus 2. And I want you to notice that the slope of this line is 2. So when you have a linear equation, another way of getting your terms is you can find the first term, right? So like I found the first term by plugging 1, I got 9. And then if the slope is 2, I know I can just keep adding 2, right? Instead of plugging in 2, plugging in 3, plugging in 4. All right, the next one right here, this is a quadratic. We're going to find b sub 1. So we're going to plug in 1 for b. We got 1 minus 4, which is negative 3. We're going to plug in 2 for b. We have 4 minus 4, which is 0. We're going to plug in 3 for b. We have 9 minus 4, which is 5. And then we're going to plug in 4 for b. We have 16 minus 4, which is 12. So our first 4 terms are 3, 0, 5, 12. All right, next one, we have find the first 4 terms. We're going to plug in 1 and find c sub 1. 2 to the first power is 2, plus 1 squared is 1, and I get 3. C sub 2, plug in 2, I get 4, plus 2 squared is 4, that gives me 8. C sub 3 is 2 cubed, which is 8, plus 3 squared, which is 9. That's 17. And then, like, instead of being the, like, I can look at it as 2 separate. Like, on this, it's doubling, right? So that's 2, 4, 6, 8, 16. On this, it's perfect squares, 1, 4, 9, 16. And I could always double check it, but that's what's happening, right? So on this doubling pattern, what I want you to notice, it's doubling 2, 4, 8, 16, 32. That is when you have an exponential function. So this is an exponential function right here. And that means 2 multiplied by 2, okay? But that we'll get more into later. So we have 3, 8, 17, 32. All right, lastly, we have, not lastly, there's more after that, I can see them. We have n factorial. So we are going to find d sub 1, d sub 2, d sub 3, and d sub 4. That exclamation point means factorial, okay? And it's the easiest way to explain it to you is that if I wanted 10 factorial, that is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, okay? So you take that number and you keep multiplying it by each number that's minus 1 from it. All right, so 1 factorial is 1. 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. And 4 factorial is 4 times 3 times 2 times 1, which is 24. So we have 1, 2, 6, 24. Once again, that exclamation is called factorial. All right, next one, we need a sub 1, a sub 2, a sub 3, and a sub 4. All right, so we're plugging in 1 for n. That'll give us a negative 1. And then plugging in 1 for n here, we get 5. So negative 1 times 5 is negative 5. Plugging in 2 for n, we get a positive 1 and 6. So that gives us positive 6. Plugging in 3, we get a negative 1. Plugging in 3, we get 7. And then let's pause time out and see if we can figure out what the next one is without actually doing it. So negative 5, 6, negative 7, 8. Let's check to see, make sure that that is it, which it is, right? So positive 1 for the plugging in a 4, and plugging in 4, we get 8, which is 8. All right, so let's see what's happening here. This, what did this do? Alternated the signs. Okay, so whenever you need to alternate a signs in a pattern, you could always do negative 1 to the nth power or negative 1 to the n minus 1 power, depending on what you need. And then notice right here, this is linear with a slope of 1. So 5, 6, 7, 8, that's increasing by 1. All right, next one, we need a sub 1, a sub 2, a sub 3, and a sub 4. All right, so I have fractions as answers, so I'm just going to make my fraction bars. And I'm going to do the numerator and denominator separate from each other. So plugging 1 in the numerator, I get 2. Plugging 1 in the denominator, I get 3. Plugging 1 in the numerator, I get 3. Plugging in plugging 2 in the numerator, I get 3. Plugging in 2 in the denominator, I get 4. Now, I could do it this way that I'm doing, or I can do all the numerators and then all the denominators. So notice my numerators are plugging in 1, I get 2. Plugging in 2, I get 3. Plugging in 3, I get 4. Plugging in 4, I get 5, because they're increasing by 1, because the slope is 1. The slope is 1 here also, so they're increasing by 1. 3, 4, 5, 6. So we have 2/3. Any fraction that's simplifiable, you should simplify. 3/4, 4/5, and 5/6. None are simplifiable, so let's just leave it. Okay, next one here, a sub 1, a sub 2, a sub 3, and a sub 4. All right, so we're going to start with our first term, plugging in 1. We have 32 times 1/2 to the first power, which is 16. 32 times 1/2 to the second power, which is 1/4. So 32 times 1/4, which is 8. 32 times 1/2 to the third power, which is 32 times 1/8, which is 4. And let's see our pattern here so far. 16, 8, 4. So notice it's taking half of each number. So 16, 8, 4, this should be a 2. And let's see if that pattern continues. So we have 32 times 1/2 to the fourth power, which is 32 times 1/16, which is 2. Okay, so, also to mention, this whole chapter is all calculator, so you could use your calculator just to throw it all in there, but this is not difficult amount of math. So what this is right here, this is an exponential function. You can tell because the variable is an exponent. This is an exponential function, okay? And when we'll get more into this, but whatever the base is on that exponential function, which is 1/2, you multiply by that. Okay, so next, given the sequence, a sub n equals n over n plus 2, find the ninth term. So just plug in 9. This is nice and easy. That's 9 over 11. Find the n minus 1 term, which I want to make sure that we know how we could also say this. This is the previous term. And let me explain why. Okay, so when we're talking about a sub n, that is the current term, right? Or the like a sub n is the equation, right? A sub n equals, that's what's happening. And like if you're plugging in 1, we're talking about our current term. The previous term would be a sub n minus 1, because 1 before n is n minus 1. So this is the previous term. And then a sub n plus 1 would be the next term. All right, so it says find the previous term, which we can say it that way, or find a sub n minus 1. So also realize it just means plug in n minus 1 here and here. So we have a sub n minus 1 is equal to, instead of writing n in the numerator, we're going to write n minus 1. And instead of writing n in the denominator, we're going to write n minus 1 and then the plus 2. And then just simplify that. So we have a sub n minus 1 is equal to n minus 1 over n plus 1. Now let's find the n plus 1 term. So we're going to do a sub n plus 1. Same idea. In the numerator, instead of writing n, we're going to plug in n plus 1. And the denominator where there's an n, we're going to write n plus 1. And then don't forget the plus 2. Clean it up, and we get a sub n plus 1 is equal to, that does not say a sub n plus 1. A sub n plus 1 is equal to n plus 1 over n plus 3. Okay, so next, really quickly, we're going to talk about patterns, common patterns, and the types of functions that are involved. These are types of patterns that you will see quite often in this chapter. So first off, we've already talked about linear. So I'm going to give you an example of a linear pattern. So if we saw 5, 8, 11, 14, 17. This is a linear pattern, which we will be calling arithmetic in this chapter. Okay, so when you have an arithmetic or a linear pattern, it increases by a constant difference. Okay, so there is a first constant difference. Difference. I don't know how to spell. Okay, so what I mean by that is that if you look here to get to the next term, this is a plus 3, plus 3, plus 3, and plus 3. So it's constant because it's the same number. And it happens on the first try, right? Like on the first row. So that is we know that this is going to end up being a linear equation. We can write one. We know it's going to be a linear equation that has a slope of 3. But we'll get into that in our next lesson on how to do that. And there's an easier way than what we did in the pattern types. All right, next, actually, I want to do exponential next because that's the one that we see the most often next. So exponential is when there is, I'll give you an example first. So if we had 6, 12, 24, 48, 96, okay? All right, so if you look here, this has a common multiplier. So that's times 2, times 2, times 2, times 2. So this is an example of an exponential function which we call geometric in this chapter. And that's when there is a constant multiplier. Okay, so this is going to end up being an exponential function, and that multiplier we refer to as a ratio. So we use ratio as the word here. Here we use difference. So the difference here would be d equals 3, and the ratio here would be r equals 2. Okay, and this is going to end up being an exponential function, so this would be 2 to the nth power, and then we would have to come up with something else to get to, we would say it would be n minus 1, 3, 6 right here, but let's not get into that. That's another lesson, okay? All right, lastly, a quadratic. That's when you have a second difference is constant. Second difference is a constant. So not the first difference, but the second difference. Then you know it's going to be a quadratic pattern, like 1 squared, 2 squared, 3 squared, 4 squared. That's a quadratic, right? So here, let me give you an example. -2, 1, 6, and I'm copying this down from something that I already did. I'm not, just randomly pulling these numbers out of thin air. All right, so if I look for a first difference here, this is plus 3, this is plus 5, this is plus 7, and this is plus 9. So now I have another pattern just happened, and now if you look here, this is plus 2, plus 2, plus 2. So this is a constant second difference. This is, well, I'm not going to put first next to it because there's no, this is a second difference. This is for 1, 2, second difference. Right? So we end up knowing that this is going to follow a quadratic equation. So this would be n squared of some sort. Obviously, it's not just n squared because 1 squared is not -2, but we could write an equation once we know that. Okay, so we have 5 examples here now, and we are going to write a formula for each sequence. This is difficult to explain how to do, especially when there is an easy, we have lessons on each one of these. We have a lesson on how to do it if it's linear, which is arithmetic. We have a lesson on how to do it if it's geometric. But I want to play around with it when you don't know how to do it yet, to show you that you can do these. All right, so let's first see what kind of pattern this is following. So if you look here, we have -3, -3, -3. So this is -3, -3, -3. So we know that this is going to be a linear equation. Okay, this is going to be a linear equation. And I know that the slope is going to be 3. So m is going to be 3. Sorry, -3, so it's -3. Okay, so I know it's going to be an equation of a line, and we're going to write them in the form a sub n is equal to, and then your slope is going to be -3n, but then I got to figure out what this number is right here. And when I plug in a 1 here, I have to get my first term, which is 7. So you could run through a little bit of guess and check, which is absolutely fine, okay? Or you can say the first term is 7, the second term is 4, the third term is 1, the fourth term is -2. So I have an ordered pair right here, 1, 7, and I have the slope is 3, so I can write the equation of a line. So I can do y minus 7 is equal to -3 times x minus 1. Y minus 7 is equal to -3x plus 3. Add 7 to both sides, and I get y equals -3x plus 10. So I know that this is a plus 10. okay? But once again, you can just play around with it in your head and say, okay, when I plug in 1, I have to get 7. Right now I'm getting -3. Oh, I have to add 10, okay? Or you could say the slope is -3, so if I want to go this way, I'll add 3, and I get the 0th term is 10, which is my y-intercept. Bunch of different ways to do this, right? I'll teach us a way that always works and is the easiest in tomorrow's lesson. All right, here's our next one. We have 1, 4, 9, 16. I notice these are perfect squares. This is 1 squared, 2 squared, 3 squared, and 4 squared. So I'm going to say my rule is just take whatever number term it is and square it. That wasn't bad at all. All right, next one. Whenever I see a fraction, I look to see if I always look to see if there's like an adding or multiplying, but there's usually not. So then I just separate the numerator from the denominator. So I'm going to start writing my rule already because I got part of it, right? It's always a 1, right? And now I just need the denominator. So now I'm going to look at the denominator like its own little separate function. Where'd it go? There it is. And I see that it is plus 4 plus 4 plus 4. So what I'm going to do, I know it's linear, the denominator that is. I'm going to write an equation of a line for the denominator. So this is my first term, my second term, my third term, and my fourth term. So I know that the slope is 4 and that there is a 0.1 comma 3 that I can use, or 2, 7. So I'm going to do y minus 3 is equal to 4 times x minus 1. Y minus 3 is equal to 4x minus 4. Add 3 to both sides, and I get y equals 4x minus 1. So this is going to be 4n minus 1, and there's my rule. Okay, and if you're like, I did it, but I did it a different way. If you have 1 over 4n minus 1, I know, it's fine. It's fine. All right, so this is my second time making this video because I didn't realize these were on here, and I think they are important to explain, okay? All right, so this one right here, I'm going to look for a pattern first. I see that this is times 2 times 2 times 2, okay? So as I explained before, when you have a constant multiplier, this is going to be an exponential function. A sub n is equal to, the base of your exponential function is 2, okay? And then you're going to bring it to the n minus 1 power. You'll see why in a moment, why I didn't do nth power. Okay. If I do nth power, right, if I do nth power, then when I plug in 1, I get 2, and I'm trying to get a 3, and it's too much work for me. So right now, if I say when I plug in 1, I get 0, and 2 to the 0 power is 1, right? So now I say this is equal to 1 when I plug in 1, and I need it equal to 3, so I can put out a multiplier of 3, which is my first term. I'll explain in a whole entire lesson on how to do that. Okay, but if you check the rest, if I plug in 2 here, I get an exponent of 1. 2 to the first power is 2 times 3 is 6. It works, okay? So that is a geometric function which has an exponential, this is a geometric sequence which has an exponential base right there, an exponential function, okay. All right, last but certainly not least, I have numerators and denominators. And if you look, these as fractions have nothing in common, but if you look at the numerator denominators separately, I can figure something out. So I have a sub n is equal to. All right, for my numerator, let's see, what's the pattern here? Plus 3. So the numerator is a line following the slope of 3. So I'm going to do 3n, okay? And then if I want to write the equation of the line, m equals 3, the first one is 5, y minus 5 equals 3 times x minus 1, y minus 5 equals 3x minus 3. Add 5 to both sides, I get y equals 3x plus 2, so 3n plus 2. All right, and if you're like, I just said when you plug in 1, you don't get 5 yet, so you had to add 2. Yep, that's fine. I'm okay with it. Down here, it's times 3, times 3, times 3. So in my denominator, I'm going to say I have 3 to that. First, I'll do nth power. When I plug in 1, I do get 3. So this works, but I could also do n minus 1 and then say the first term is 3. I can do that. That works. Or just this works. Lovely. All right, and there's your rule. Okay, you should try some homework on your own, and we'll see